So you guys just took your IMF quiz, or you're about to take your IMF quiz, depending on what year this is. And we spent a lot of time yesterday going through the warm-up draft, just talking as a class, using our IMF knowledge, our intermolecular force knowledge, to explain why certain substances experience certain properties, experience better fluidity, experience specific states of matter at room temperature, and so forth. And particularly, we put this with the idea of how can we, using IMFs, explain and identify the identity of the unknown substances used in your penny demo lab. You had 3 substances. I didn't tell you what they were. They all looked like clear liquid, right? And what we had to do is we had to figure out, well, based off of the molecular structure, Lewis structure, and polarity, regions, if any, of unequal sharing, regions of partial charge, what type of IMFs could each molecule, out of the options of identity, could each molecule experience? And based off of the type of IMFs, we were able to determine if I have stronger IMFs, I have higher drop number because I'm having higher surface tension, right? Having higher surface tension, which is the resistance to spread, because I'm having higher molecular interaction. And that also matches with the idea that I would have a higher boiling point and higher melting point, because it would take more heat energy to spread those particles apart of that substance. So what we did is, according to what should have happened. Now remember, your data is your data. Please do not lie about your data. But you should have technically gotten that substance 3 was water. Highest drop number, highest intermolecular forces. 2 hydrogen bonding capabilities, plus dipole-dipole, plus LDF. You should have gotten that substance 1 was ethanol, second biggest dome, second highest molecule interaction, second most intense or strong IMFs. They had H bonding, okay? It had dipole-dipole and an LDF, but it had 1 less H bonding capability than water, 1 less HO structural bond, okay? And then you should have gotten that substance 3 was hexane, a giant non-polar chain, a giant CH chain that literally is banking on temporary electron movement. The only reason it has any type of stickiness, any type of IMF, is because it's got a lot of electrons present. Sometimes it's just about number count, right? More electrons in general, the more possibility you have, even with random electron movement, to kind of influence other polarities to form randomly, temporarily, instantaneously, okay? So we drew particulate diagrams. Your task for this draft is that you are going to clean up my model, okay? This is all kind of messy. You can change it if you want it. You can add different colors, whatever. But you are going to now label, okay, on the penny, whatever you do. I don't care what order you go in, but you're going to, maybe you go from weakest to strongest. Maybe you reorder. And you tell me the substance and its identity. So if this was me and I did it weakest to order, I would do substance, okay, 2, hexane is the weakest. Substance 1, ethanol, was the second strongest. Substance 3, water, was the third strongest. Sorry, hold on, the most strong. Then I'm going to label all of the IMFs present. So for hexane, I'd label LDFs. For ethanol, I'd label all 3, and I'd specify that I only have 1 H bonding. For water, I'd label all 3, and I'd specify that I have 2 H bonding. And I'm going to draw a particulate diagram that shows. And remember, for ethanol and water, positioning matters. You actually have to pay attention to that in these 2 particulate diagrams, okay? And then I'm going to write up a CER. And I'm going to answer the question, use your notes on IMFs and the data you gathered. So your data, like your average drop count. I want your average drops. Like I want numbers in here to explain why substance, okay, it should have been 3, but maybe not for you. I don't know. Maybe it wasn't 3 for you. You have to identify. Okay, has the largest dome. Why substance 3 water? Maybe for you, you thought substance 2 was water. You have to explain that. Okay, has the largest dome. And I give you sentence frames. Sentence frames, okay? You don't have to use all of them, but you probably need to use more than one because look at the grading. To get an 8, you're going to, one, have to answer another question. But to get bare minimum B grade, this is a B grade, okay? You have to, one, have your model be accurate. You have to have, this is also part of the model, ranking the solutions from strongest to weakest. This is also part of the model. You have to identify each solution. And then this is also part of the model. You have to label which solution was substance 1, 2, and 3. And then you have to explain, which is the CER. Okay. And that CER definitely has to include IMF and physical property connection. Physical property connections. You have to show me the relationship between them clearly. And of course, you probably definitely need to use the actual numbers, your data in your CER. All right. So, this warm-up took way too long today. I'm going to give you the rest of the class after I introduce tomorrow's lab really quickly. So did everyone get this? Okay, so now let me ask you to switch over to the lab. So you can download it on Canvas or my agenda. Now let's switch over to quickly introducing you to tomorrow's lab, which is the start of a 5-day project where you guys are going to explore how intermolecular forces and your knowledge of their connection with physical properties explains plastics, all the different kinds of plastics out there, right? So for this lab, there's a ton of background information, okay? I'm going to ask that tonight you read the background. It's 2 pages, and then tomorrow we will warm up with these questions. But I'm going to ask that tonight you read the background, page 1 and 2, and answer the check-in questions. And then I'm also going to ask that you read the procedure. Tomorrow's goal is all about mass quantity making. So I really need you guys to know what the procedure is. And it's pretty consistent. Like if you read one, you kind of know what everybody else looks like. It just is slightly different ingredients and maybe one additional thing. But the process pretty much stays the same. When you come into class tomorrow, we'll do a 10-15 minute warm-up. Make sure everyone's on the same page of why we're doing this. And then a couple of tricks of how to do it. And then I'm just going to throw you in lab, and it's about cranking it out. You're going to try to fill up molds and molds and molds of plastics, because the more plastics we have, the more likely your project's going to succeed. Okay. So that's your work tomorrow. The background gives you an idea of how we can actually apply and see hydrogen bonding, dipole, and LDFs as the explanation for why we get various plastics. And we're going to try to take advantage of all of that using natural ingredients so that hopefully it's better for the environment. We're calling them bioplastics, biology-based plastics. So that's tomorrow. You guys have the rest of class to work on the penny demo or work on this, and good luck.